Started here. This should pop up in a second. Sorry, getting a little bit of a late start. I underestimated how long this walk is. I had too many students try to bombard me after my last section. So, couple things off the top. I want to make sure I don't forget to mention. So, go with SCADA, getting that working on your device. If you're having any issues or difficulties, I think it's office hours tomorrow would be a really good time to kind of stop by and kind of work through them. The two most common issues that I've been seeing and that people have sent me are the first, and I walked through this on day one, Tuesday, so it might have gotten kind of forgotten because I didn't go back over it Thursday. We need to make sure that you go to your, you go to one.iu and then on the cloud storage, so find cloud storage, you need to make sure that you have that OneDrive IU authorized and has like a green check mark next to it. So that's, I think, causing a couple of the issues. The other one is you have to use the file. I think the files that you're using, and I inherently forgot about this because I have to do it up here, have to be on your OneDrive. So I think for some of you, there are some issues if you're trying to open the files off of your desktop. So you'll have to create like a 371 folder or something on that OneDrive that you've authorized, and then it should be able to open files from there without an issue. So those are kind of the two things that I think are, at least that's honestly the only error messages I've been sent. And if you sent me an email, I haven't responded to you since Friday. I will get to those this afternoon. I was a little busy this weekend, didn't get quick responses out to a lot of those that I saw coming in over the weekend. So if you haven't heard back from me, you should this afternoon. I'm going to kind of check off all those emails I came in over the weekend. Okay. Just a couple of other things I wanted to mention, because I had some people approach me after class and I hadn't thought about maybe it's being explicit. When I have these do files that we're using in class, I'm not expecting you, like they're up there and they're already typed out. I'm not expecting you to kind of retype them. Like I'm not going to go that slow probably. So one thing I might do, I kind of showed you how to do the comments by doing the 2 backslashes, maybe having it open. And then anytime that there's something I say, or maybe we add some additional code in class, maybe type that in. All right, so you don't have to like reproduce the entire do file in class as we're working through it. You can add to it, right? Maybe some comments and things so that when you're going back and reviewing it, I try to put in comments that are helpful, but each mind is different, right? So maybe there's something I say in class that connects with you a little bit more about what that line of code does, and maybe you want to kind of put in a comment there so you can have it saved. That's kind of how I would take notes almost when we're doing the do files. Like you could do it right in that do file by using that double backslash to put in comments. Okay. Also, a reminder, I will use kind of the Canvas for those in-class quizzes. So we might, wink, wink, have one on Thursday. So, so once again, I think a little bit low in attendance here today. I can't highlight enough how hard it is. If you fall behind in this class early, it's going to really be tough to kind of get back. Okay. Is there anything else I wanted to say? Oh, I will get up a set of practice problems after class today. And that will be for that first quiz, which I'm going to have set to be released after Thursday's class. So it'll just be kind of a review of statistics, the stuff that we talked about last Thursday, as well as this week. Shouldn't be anything too crazy. And then that will be due before we meet in class next Tuesday. After class Thursday, I'll also get up the very first STATA assignment. So it'll be pretty basic. A lot of the stuff that we worked on this week, a little bit we worked on, or I showed you kind of on Thursday. You'll have 2 weeks to turn that in, so a lot of time to kind of work on that. I realize it's the first time you've been using this program, even though it's not like the most lengthy assignment, it still might take some time to kind of get going with that. So those will both be available after class on Thursday. And that should cover for me. Any questions for me before we kind of get started diving into material here today? Excuse me, all right, that might be something at the end. So I've got the skeleton slides for this week up there, so we'll start kind of working through those. The do file, we'll kind of go back, revisit that review of statistics, kind of finish up on that today. And if we have time, I will dive into that NBA sample distribution. I'll work with that kind of towards the end of class. So if you want to, kind of ahead of time, also this kind of used to. So I had this pulled up, right? I went to IU Anywhere. Well, first I went to one.iu, then I went to IU Anywhere. I selected from the app menu, STATA, we got that opened up. Here's the actual program. Here's the actual do file, right? So I don't have anything open, so let me go here. I want to open from my OneDrive, fall, here. No, it's under week 2. Review of statistics. And then later on, we're also going to this is a good time to show you this as well. So if you're having issues with opening the file, so let's say I'm going to download this data file, go back, going to download this view file, and I'm going to go to oh, this is my OneDrive. So, file explorer, downloads, copy these. I downloaded the wrong one. Yes. Hold on. Sorry. I make stupid mistakes too. We already have the review of statistics one. I needed this one. There we go. Now I go to my downloads, view file. I go this over here. Even though we're not going to start out with it, this one I have pulled open when we get there later in class. We're going to go to open. Now we've got that view file in there. So these are going to be the two view files that we use for the class. So this will be kind of the procedure even you would use, right? Download them from Canvas. They'll get thrown in your downloads folder. Just move them over to your OneDrive, and then we can have those view files opened up and ready to go once we get there. Okay. You'll also want to drag the data files that you're going to end up using, just kind of like I did, also into that OneDrive. So anytime your view file tries to open a data file, that data file also needs to be in that OneDrive folder. And like I said, I've got it kind of broken down by section and weeks and things. You can just throw it all in 371 or whatever kind of works best for you. All right. Any questions before you kind of dive into the material? We're not going to start out with state of here today. Okay. So we left off thinking about the normal distribution. Grab your slide around a bit. And we said it's going to be defined by two things. The first is going to be its mean. The second is its variance. So we had this. Oops. So we kind of can write. We've got some random variable. We can calculate its mean. We even saw how we did that in Stata last Thursday. We can also calculate its variance. Now I kind of went through and I showed you some slides where like there's a 68% of the data is within one standard deviation, 99% is within 2, kind of so on and so forth, or 97.5 is within 2, so on and so forth. So where did that come from? Well, it's something we're going to look at today. Might kind of ring a bell, like z-tables or this standard normal distribution. So we also looked at last Thursday, well, how do you standardize a variable, or how are we going to create these, what we call z-values, right? We said we're going to do what? Subtract the, you don't remember how to standardize the mean, and then you divide by, did you guys calculate z-scores from 370? I know you did. Subtract the mean and divide by the standard deviation, right? So we can kind of create these z-values by like these standardized values by subtracting the mean, dividing by the standard deviation, which would then have this nice standard normal distribution. And there's a function to it, we can start to do, some integration, right? So I could say, okay, look, I've got a z-score of -2. That means I had a value that was 2 standard deviations below the mean. What was that likelihood? Like, what was the probability I saw something that far away from the mean or something even further away, right? We can find the area to the left of that z-score of -2 by using integration. Now, I'm not going to make you do integration. Someone's already done this for us. Once we have these standardized z values, we can look them up in this table, right? And I'll hold this open here in just a second, but we'll kind of walk through on the slides first. So these z-scores are essentially standardizing the variable x that you're interested in here. Its number just represents how many standard deviations above or below. If it's negative, it's below the mean. If it's positive, it's above, right? So hopefully this is sounding, somewhat familiar. We at least talked about this a little bit in your 370 or equivalent. But these z-scores are going to be helpful for us. They're going to lead to things that we'll use a lot, like p-values. So standardizing variables, I won't waste too much time here because we did do this last Thursday. All right, I'm thinking about now the mean of this z-value. Well, the expected value of my y value, when I say expected, that's just the mean. So the mean minus the mean will always be 0. So that's why when we subtract the mean, our new variable, our new standardized variable, or the z-score, will always have a mean of 0. And then you can kind of work through the math if you want to do the expected value of z minus the mean squared. That's always going to end up being 1 when we kind of subtract the mean and divide by the standard deviation there to create that z value. The math is a little bit harder here, like you have to break z down into the different components, but it will always simplify down to that the variance is 1. So that's what we need, a standard normal distribution to use those z tables. I wouldn't worry too much about kind of writing this notation down. Just knowing that it has these z values have a mean 0, variance of 1 is kind of key. Now, also having a variance of 1, what's the standard deviation? How do we get the standard deviation from the variance? Square root. So the square root of 1 is 1. So here, the standard normal, our variance is our standard deviation. It's kind of weird. So like even when I'm saying like, I guess technically, you could interpret the z-scores and standardizing a variable. It's not, let's say I had a -2, it's 2 standard deviations below the mean, but it's actually also 2 variance, like it's 2 of the variance below the mean as well, because they end up being the same thing with these standardized standard normal distributions or standardized variables. All right, we did that last week. I'd like to get this to work. Not sure why it's not. All right, so these normal distribution and the standard normal distribution, why do we care, right? Well, first of all, we see the normal distribution pop up a lot, like in the real world. So I've got a couple examples, and the best one, I shouldn't say the best ones. Biological statistics often have normal distribution. It's like kind of uncanny. So IQ, height. I had a data set of a bunch of adults. It's from some survey called, NLSY, National Survey of the Youth. They said it was adults, it wasn't the youth because they followed them for like 30 years of their life, right? So I took a year when they were all adults, looked at the height, and I think it's either male or female height because I'd have kind of different means there. But this is really, pretty symmetrical distribution, right? This is pretty close to a normal, and it's not even that granulated, right? I kind of have these like little bins as opposed to like every single possible decimal measure of height. I saw this also and kind of geeked out. I'm not really into CrossFit, but I saw something that they put out on social media and was like, wow, that's pretty cool. So this is like performance on one of their events or something. And this is like almost a perfect kind of normal distribution. Now this was like only the elite athletes, obviously we took like the general population as a whole. It might look a little bit different, right? When having a long right tail there, they have some skewed distributions, but kind of human performance we see often follows a normal distribution as well. Like I said, I think I mentioned IQ, all these different biological statistics, a lot of the times we'll see these nice normal distributions. Now, while they're useful, the function for a normal distribution is kind of crazy. So if we want to find the probability, let's say I'm selecting a person at random, and I want to know what's the likelihood that they have an IQ in between 100 and 110, right? Some range. Right? Well, I have a function for a normal distribution that in it has the mean and the variance. but we don't want to have to do that math every single time. If we can just take those two values, turn them into z-scores, we can then use this like the work done, all this previous work done to have this integration to be in between this many standard deviations of the mean. So we're going to take these two values and we're going to turn them into z-scores and then use that in the table. So what the table is going to tell us is always going to be whatever z-score we look up, the probability of seeing that z-score or a value that's that many standard deviations away from the mean or anything below it. So it's always kind of telling us the area to the left of whatever value we look at, if you want to think about it that way. So if I had a z-score of negative 1.29, the table is telling me the area under that normal distribution curve, or the standard normal distribution curve, to the left of negative 1.29. And it kind of goes off into infinity. So it works out to be pretty close to 1.29 is close to 10%. So it's kind of a benchmark that we often use. At 10%, 5%, and 1%. So you'll see this value start popping up a lot throughout the semester with one caveat, which is we're going to later talk about two-tailed tests as opposed to just one tail. But here, how am I getting this value? So here's the table. I have this PDF up on Canvas. You could pull it open if you wanted to right now. I'll show you here in just a second, but it looks just like this. I mean, I literally screenshot the PDF and put it on this slide. So if I wanted to look up that z-score of negative 1.29, the left-hand side, the first column, tells me the first decimal, and then the top tells me the second. So there's also two sides, or in the PDF, two pages to that z-table. So the first is all negative values, the second is all positive. Okay? Now, if I'm just thinking about the area to the left of a z-score, if I have a standard normal distribution that's perfectly symmetrical, what should the area to the left of 0 be? So the standard normal distribution, its mean is 0. We said for a symmetrical distribution, the mean is the same as the median is the same as the mode. So if the mean is 0, the median is 0, which means that it exactly splits the data, or that there's 50% to the left, 50% to the right. Sure enough, if I look up 0.00, the area to the left of that is 0.5, right? And then as I kind of start to go away from that point of 0, so maybe I want to go to negative 1.29, well, I find the first decimal, so negative 1.2, then find the second decimal, which was, negative 1.29, go to where those two meet, and the table tells me the probability of seeing that z-score or anything to the left. So I looked up negative 1.29, sure enough, I get that value is really close to 10%. I have 0.0985, as close as I can get without extending this to be like a three-dimensional table with a third decimal, going out to the thousandths place, right? We'll only ever kind of keep things at that second decimal. Okay? Now we'll see how we can kind of use Stata to kind of get at any level. But for starting out, this is how we'll kind of approach it. And this hopefully looks somewhat familiar. You did this, and maybe you use Excel in 370 or the equivalent to do this as well. Any questions on this before we keep moving here? Shouldn't be too bad yet. Now the other half has the positive values. So this is where, if we think a little bit harder, we can actually come up with this without even looking up the value in the table. If I were to look up positive 1.29, what should the area to the left of that be?
1 minus the negative.
Yeah, right, because the area to the right of positive 1.29, it's symmetric. It has to be the same as the area to the left of negative 1.29. So I know the area to the right of 1.29 is 0.0985. So the area to the left of it, well, the probability of being anywhere under the curve, some value of the area under the curve always has to be 1. So 1 minus that area to the right would give me the area to the left. Sure enough, if I look up 1.29, positive 1.29, the area to the left is 1 minus 0.0985. Other questions on that before we keep moving here? Okay. So I already kind of went through this. All right, we already talked about this. This would be the big one, right? I can look that up and find the area to the left of that. So I'm thinking about here, if I gave you a question like this, right? Sometimes I'll put these questions and just kind of think about how we would be applying this. If I want to know what's the probability that z is greater than or equal to negative 2.53. Now, first of all, which of these can I hopefully rule out right away?
Negative.
Yeah, the table, the area to the left of a value at the very least has to be zero. I mean, even zero, I'd have to actually have negative infinity, so it doesn't even make sense. So it has to be some positive value, right? Now, we looked up negative 1.29 and we're already at what, 0.0985. So if I go out to negative 2.53, the area to the left of that should be smaller, right? Now I want the area to the right, so what am I gonna have to do? Whatever that area is, just 1 minus that. So I'm gonna have a pretty large value. So the only ones that really make sense here would be A and D, and A doesn't really make sense because if I'm almost at 0.5, what would my z-score have to be? That's such that there's only pretty close to zero, right? So if I'm just guessing, looking at these values, the one that makes the most sense, D, right? And sure enough, I don't know if I actually put a picture up of it, but if we go here, where's negative 2 points? So negative 2.5, 3.0057, subtract that from 1, 0.9943, okay? Any questions on what I did there? I know it kind of had some handwork, I'm just kind of talking through without giving you as many visuals on that one, but shouldn't be too bad. And then what if I want the probability being less than that? Well, I don't have any extra work to do there, right? I would just spend that 0.0057. Okay. So we'll see a lot of these z-scores pop up throughout the semester because we'll start talking about things like confidence intervals, hypothesis testing. So we have these benchmarks like 10, 5, and 1% a lot. So they kind of correspond to some of these z-values. So I just put these up here. These will be values you start seeing pop up a lot throughout the semester that we're using when we're doing hypothesis testing and building confidence intervals. And you'll notice they aren't perfect, right? If we're taking to the second decimal, we're a little, this isn't quite 99% or probably 0.99, or this isn't quite 95% or probably 0.95, but to the second decimal, that's as close as we get. Okay? These values looking familiar from 370. So let's say I had a question like this. This might be an example of something I use for like an in-class question in Canvas. And just kind of talk through this, right? Just seeing more examples I think sometimes helps. So let's say I've got some movie, Mr. Nanny 2, based off the success of the original, and I've got demand being normally distributed with a mean of 50, variance of 100. So my standard deviation would be, trying to make these numbers easy. So yeah, take the square root, my standard deviation is 10. So if I make 60 pounds of popcorn, what's the probability that we won't have enough to meet demand? So essentially, the only way that I don't have enough is if demand is greater than 60, right? So I can kind of think about visually what I'm doing here. You don't have to necessarily draw this out for yourself. Does this have a really bad glare on it? Is that easier to see when it's up now there? We'll see once I start writing. See that okay? Okay. So we just said it's normally distributed, mean of 50, variance of 100, right? So what we're really trying to do is say, okay, look, if demand is 60, what's the probability that the actual kind of value for X, for popcorn demanded, is something above 60, right? What's the likelihood we didn't make enough? Well, what I'm going to do is take that normal distribution, and essentially I'm converting it into a standard normal distribution or using these z-scores. So I know that my mean, once I standardize it, how many standard deviations away from the mean is the mean? 0, right? And then we always said our variance or our standard deviation, once we standardize, will always be 1. So now I'm going to turn 60 into a z-score. How do I do that? I subtract the mean, divide by, we said our standard deviation was 10, divide by the standard deviation. I get a z-score of 1. Okay? I'm then going to look that value up in my standard normal distribution table. It will tell me the area to the left. I wanted the area to the right, so I need to then, whatever value I find from the table, subtract from 1. Okay? Any questions over any stuff there? Okay? Shouldn't be too crazy. Well, automatically, I know this probably has to be less than 1. what would the area to the right of the mean be? 0.5. So the area to the right of 60 has to be less than that. So that's just something I can do to prevent myself from forgetting that last step of doing 1 minus, right? So I know that it has to be less than 0.5. Before I even go through all those steps, right away, I should cross out A, right? And cross out D, right? No, or actually, no, sorry, it could technically be D, but with 1 standard deviation, we've already worked through some examples. We know it's not going to be close to, the probability is going to be a little bit further away from 0. So if I look this up in the table, so go back here. So 1.00. So anytime I have an integer, the decimals are zeros. So I get what, 0.8413. So this is where, if I remember ahead of time, oh yeah, it has to be less than 0.5. I don't accidentally say, okay, yep, I looked it up in the table, it's 0.8413. Well, no, you wanted the area to the right, so you still have to subtract it from 1. So we get what, about 0.15, 0.1587 there would be the answer. Any questions on that before we keep moving? And this was an actual movie with Hulk Hogan, so if you haven't seen this, I mean, it's hilariously bad. So if you want a good laugh, this is a great movie. What if I want the probability that it's over 600 or under 400 or 600? Over 60 or under 40? Well, I actually already have all I need, right? So we just said the area or the probability of saying 60 or more was 0.1587. What's the area going to be to the left or under 40? Same exact thing. Why? It's the same amount away from the mean. It's 10 away from the mean. It's a symmetric distribution. So if I looked up how far away would 40 be from the mean, it's 1 standard deviation below, right? 10 away. So I now look up -1. It's symmetric. I'll find that same value of 0.1587. Now we can prove that to ourselves if you go back to the z tables, but if it's standard normal distribution, it's perfectly symmetric. It'd be 0.15 in that kind of right side, 0.15 on the left, so below 40. Add those together, 0.3156, 0.3173-ish, right? I'm rounding the 4th decimal here, so it gets a little bit. Any questions on that? I know I'm just kind of talking through this, but hopefully this is still kind of you here today. And that's a screenshot. So we can also do something called the inverse transformation. Okay, so I'm calculating these z-scores. And a lot of times, yeah, maybe I do want to know, well, how likely is it that I see this value for x or something below it or something above it? But a lot of times you might say, okay, what's the cutoff for like the 90th percent, right? Or the 90th percentile. So if I have my z-score equation here, if I just rearrange this, right? This z-score I can think of is always associated with some probability, right? When I look up 1.29 in that table, it's always going to tell me that was it 0.84 something was to the left of it, right? I'm always going to find that same value. So every z-score is associated with a different probability, right? An area to the left. So if I just rearrange this, so I multiply both sides by the standard deviation. So I've got, and then I add the mean both. I'll end up with, I can figure out these cutoff values for x that would correspond to different probabilities, right? So once I know I want the probability of 0.9, right? I want to know what that 90th percentile is. And I'll go back to that dot can here in just a second. I can go files, tables, open it up so I can have it there. It's a little bit bigger. So I can also work in the opposite direction. Before I was showing you looking up different z values. Let's say I know I wanted that 90th percentile cutoff. I want the probability, I want the z value that the area to the left of it is 0.9. I can hunt in the middle here, these probabilities, to try to find 0.9. Okay, it looks like, all right, I'm kind of in between two here. So 1.28, and 1.29 would be the corresponding z-scores that gives me about 0.9. Like I said, once we kind of get later in the semester, we're always going to truncate these to the second decimal. I always going to say if you're in between two here, use the higher of the two, right? So here we're just going to round up and use that 1.29 because that gives us the probability that really close to what we want. So what would I then do? I now know this is the z value that I want. Let's say I use the popcorn example one. My standard deviation was 10. My mean was 50. So I have what? 10 or 12.9. So 62.9 would approximately be the amount of demand for popcorn that would kind of be my 90 percentile cutoff. Okay. So I can work backwards as well, right? Knowing that I want this probability, what's the x value for this variable, or the value for this x variable that would be the cutoff that gives me that probability. Any questions on anything here before we keep moving? Okay. So, like I said, hopefully not too bad yet. Oh, we have the time. Oh, we're good. All right. So we're down here. You know, it's I did the algebra for you, right? But here's our kind of inverse formula that we can use. I could use an exam score one. So here I want to know what's going to be the top 10 percentile cutoff. Well, it's the same thing as saying, you know, they're being 90% below. So we actually can use the same value that we just looked up, which was 1.29. We then have a different mean, right? This mean of this test score, let's say test score or an exam, yeah, it was a 72, and the standard deviation was, well, the variance was 64, so square root of that, variance was, variance 64 gives us our standard deviation of 8. Now it's a matter of plugging those in, right? We looked up that 1.29, it's just a matter of plugging those into that inverse formula, and we get that the test score that would be in the top 10% would be an 82. So hopefully that's not true for the exam in this class, right? Hopefully it's a little bit higher. Well, you know, I guess depends on where you fall in the distribution, I guess, where you want that to be. So, any questions on this before we keep moving? Good with this? So I wanted to, we'll take a break because I want to talk about sampling distributions and data, but I wanted to finish up some stuff that we didn't get to last class. So let's go back to that review of statistics. Let me zoom in a little bit so you can see what I'm doing. And if anything's ever too small or you're having a hard time, let me know because I forget to do this sometimes. So I'm gonna go up here. Up here. So we want to open this election data. So I already forgot what my path is. So we'll just use this method. So I'm gonna go to File, Import, and then gonna go. I know this. You looked at week 2 files, there's an election data file, and it has like the XLS, right? It's an Excel file. All right, so I'm gonna open up an Excel spreadsheet. I'm gonna go to Browse. Well, kind of cheated here. So let's say I go back to, I find my OneDrive, I find the folder that it's in, 371, and putting everything in the other section, just so I don't have duplicates and wasted space. Sure enough, there it is, that election data. Now, for you, you're gonna have to download it and then put it in the folder that you want to use. Okay. Questions up to this? Yeah. Yeah, so you don't need it for this part. I would always, kind of just good practice though, whatever do files I have pulled open, just have those pulled open as well. So that review of statistics one, that actually looks like, I think it still looks like it's in week 1. We started with it last week. That's the one that we're going to start out here with. So the way that you open a do file, well, I'll show you after I open the actual, import this, right? So importing my Excel file. Now, one thing I have to remember to do with an Excel file, and I think maybe this came up last week, maybe not, because it doesn't really happen with a CSV. But if it's an Excel file, notice it's trying to treat that first line like it's an observation, but this is actually the variable names. So it knows a lot of the time that that's how Excel spreadsheets are set up. So there is an option where you can say, treat that first row as variable names. Okay. And then I'm gonna hit OK here. Actually, no, I don't want the raw data. So this is another good thing to point out. There's gonna be some weird, I already noticed there's like missing stuff. I was like, what's going on here? I actually cleaned up this data file so that it was a little bit more usable for this class. So there's actually an Excel workbook. I don't know how familiar every single person is with Excel, right? You can have multiple worksheets. So you can actually select the worksheet you want to import as well, which is what this option is. I don't want the raw data. I want the non-missing. This was the one that I cleaned it up. Okay. So change which tab. We're kind of pulling from that election data file. Import the first row as variable names. Now when we hit OK, it gives us this line of code, right? So copy that and paste it here, just so I have it saved. So anything that pops up in this, program, the actual state of program, it's not getting saved. There's nothing here is getting saved. So I will often take that code, put it over my do file so that I kind of have that, so I don't have to restart from scratch over again. I know now the code that will import that file for me. So I've got this Excel file now open. The other point was kind of then, how do I open the do file? I can't, actually, this might not be true. I think I can open do files from here. I just often don't. Yeah, so you can open the do file from either the do file editor or from here. And I know that if you're on a Mac, it looks a little bit different. Your files, because of the way the Mac is, right, it always has your Apple and then the file and stuff like that on top. So where you see, and I got a question from another section, this toolbar here, to my working knowledge, and I looked on help boards for a while on Friday, I don't think there's any way you can get a Mac to look exactly like this, because this toolbar is always at the top left of your screen if you're on a Mac. I don't think, at least to my knowledge, especially working off of the cloud Stata, there's no way to throw that toolbar on the Stata, right? So yours is just going to look a little bit different, but you still should have the same options, right? You should have file data. They should all pop up when you're having Stata open. They'll just kind of show up here. Right? And then this looks a little bit different on a Mac too. There's all these different icons. So if I remember right, you go to edit. Oh, I have it. I'll have to do it from Mac because I forget exactly what it is now. There's a way you can go to settings and change. Oh, I'm not going to see it because I'm not on the Mac. I'll put up a little walkthrough on a little file on how you on a Mac. You will see all these icons, but some of them might not be there. There's a way you can customize your toolbar. Like I said, it's there's a thing where it's settings, and then you go into toolbar, customize toolbar, and you drag and drop icons, because Macs, you can drag and drop these icons to put them on your toolbar. But it is going to look a little bit different if you're on a Mac. You're always going to have that top toolbar that you see me use in class up in your upper left corner when the program's open, and then the only toolbar you see in Stata is going to be this second one here with all these different icons you can select. But you should have the main ones, you should have the viewer and the data browser all kind of by default, but you can add in additional icons too. Like I said, I'll get up a list when I'm on a Mac. I know exactly how to kind of walk through it and kind of put that together. Okay. Any other questions from me? Yeah.
I don't think we can upload the do file onto the OneDrive. It doesn't let us.
We'll let you put a do file on the OneDrive?
Yeah, to open it up.
So you have it downloaded?
I have it downloaded, but I can't upload it onto the OneDrive.
So when you try to drag it over and drop it in OneDrive, what does it tell you? Touch me, because you should be able to copy and paste files into your OneDrive folders. Doesn't matter if it's a do file, doesn't matter if it's an Excel file. Did other files drag over?
The Excel file is fine. Yeah, Excel works. The do file doesn't, and the data.
Do you have it? So your issue might be double check that you have your cloud storage authorized, because it might not be recognizing programs that you have access to through IU. But I can try to help you after class. But it should allow you to kind of drag and drop files of any kind once you kind of have that authorized. Of any program that the university has on that app list. Okay. Any other questions up to this point? So I just wanted to kind of walk through a few things. Review of statistics. So we got this pulled open. I'm going to kind of just rename some of these variables. So this is where it's not a productive use of your time or class time to make you retype all this out. this is just making some of these variables a little bit shorter and easier to type out or to kind of think about. So I had some old election data, and we'll have to look here in a second. I think it was by county. But it was the percent that voted for Donald Trump in 2020 and the percent of that county that voted for Biden in 2020. So I just kind of rename some things here. Now, this is the same line of code once. So I'll just kind of twice. So if I run it once and I try to run it again, notice I've already renamed this variable. This percentage 20 Donald Trump doesn't exist anymore. The only variable that now exists in my data is this. Oh yeah, I now call it Trump 2020, just so it's a little bit shorter and easier for me to kind of identify. So if you try to rename a variable that doesn't exist, it'll kind of give you an error. Well, I don't need both of these. I could just delete one, or if I don't feel like deleting, I can always just throw that double backslash in there to kind of, it can't run. It's just a comment now. It's not actual code that will be ran. I'm also going to rename the Biden one. So I'm going to select that. So I've now got in my web browser both of these two variables. Percent, or I guess it's not percent here, it's what? The proportion of the county that voted for Trump in 2020 and the proportion of people that voted for Biden in 2020. So I'm then going to go think about, okay, we talked last class, I think I mentioned conditional means, like so if I'm thinking about the distribution of height overall, it has a very different mean than if I say condition on what's the average height given that the individual was male. Because I know males on average have a higher average height than females, and so conditioning on different factors could change that mean. So I'm going to think about in this context, like just kind of identify like what's going on with voting like behaviors. Right? This is a very crude, by no means. So did I walk through the intellectual diversity thing last week on Tuesday? I don't think I added to this class. I only added to my big intro courses. I'm going to make statements about political issues. I don't like any of them. Okay, I don't care. Like we can analyze these different political issues with our economic skills, and econometrics will make us even more helpful. So what I'm saying here, we're going to take a very dirty, like a very basic glimpse into this. By no means, I think what's going to come out of this is that high unemployment counties tend to vote for Trump, if I remember right. That by no means I'm not saying that's a causal relationship. I'm just saying we're taking a look at the data. We're going to dive into these issues. I trust me. I'd like to be as unpolitical as possible. But some of these issues might look political. It's just that that's data that we're working on. Okay. All right. That's my spiel. So I mentioned this. Well, we'll skip this here. I'll show you a nice and easy one. So one way I can get an idea of like the distribution of data is really quickly is this hist command. So I think if I remember right, it's actually going to be up here. You go to statistics, summary tables. I don't even remember where this exists anymore. It might be somewhere down here, but it doesn't matter because I'm giving you the actual command, right? So you can get a histogram, which is essentially it just takes the data and puts it into kind of ranges and gives you like a nice little kind of first glimpse into the distribution of that variable. So I'm going to use this hist command. And then what variable do I want to look at the distribution of? So I'm going to put this unemployment variable, which I believe if we look here, and this is another good way, I don't want to like scroll through, I've got a lot of variables in this data set. I put it at the end to be nice, but I don't want you to have to like scroll. If you know kind of what variable you're looking for, or when it might, oh, unemployment, there's a variable called unemployment, I'll click on it, it takes you right there. Right? So it looks like my unemployment is in percentages, but it's in percentage format, not proportions, like my kind of voting variables were. So here is kind of the percent unemployed in these counties. So what I'm going to do is do hist this unemployment variable, run that code. It's then going to think for a second, spit out at me what that distribution looks like. So it's kind of, it's got a longer right tail. This is probably going to be like there's some counties with extremely high unemployment. There's going to be a lot of those like around large inner city areas, and so I'm going to have this really long right tail. I'm always going to be truncated for the left tail, right? Because I can't see unemployment below zero. It's as low as it possibly could be. So here's my variable. This is kind of a nice quick glimpse at it. That can sometimes be helpful. I might ask you to kind of just create a histogram on that first assignment. It's very easy. It's just that hist and then what variable you want to see the distribution or that histogram of. Now, I can also from this distribution kind of get an idea of probably what type of skew existence is. So if I'm looking at the unemployment variable, what's probably true about the relationship of the mean to the median? Well, I just said it looks like it has kind of this longer right tail. There's some counties with extremely high values.
So you go to the right.
Yeah, so that those high values are going to pull the mean up, but they're still counting just as one observation, so it doesn't impact the median near as much. So my mean is going to be much larger than my median when I have this long right tail. And then the reverse would be true if I had a longer left tail. Okay. Any other questions? I also mentioned that sometimes we can use these built-in functions, right? So EGen, generate was like when we were creating different variables and we could set them equal to a certain number, or we could, that's how we created the standardized. We took the variables, we subtracted the mean, we divided by the standard deviation. That was just the gen command. EGen uses these built-in functions that are like existing behind the scenes in Stata. So EGen, and then I'm gonna have it calculate my mean. We think we did this last Thursday. So I'm going to call it the unemployment mean, and it's just going to be, this is my new variable I'm creating or generating, and it's just going to be the mean of this unemployment rate variable. Okay, so I kind of hit my execution there. Sure enough, I've got this new variable, and it always puts the variables you create like at the end of your data set. So if you ever want to go look at them, they're not in alphabetical order. They should always go to the end of your data set. So it looks like the average unemployment in 2020 was about 6.3. Okay. So what I'm then going to do, let's go back to my do file and say, okay, I want to create this indicator. And I have an idea about what the mean of this unemployment rate variable is. So I'm going to call this a high unemployment rate county if it simply has an unemployment rate that is above the mean. Okay. So I'm going to say, look at the actual unemployment for that county. If it's greater than this variable I created, which was the unemployment mean, which is just the same value for everybody, then I'm going to create this new variable, generate this new variable called high unemployment. Now, it's not going to be the difference. So anytime I use this gen command, if I put things in parentheses where I have like what do we call this? Like a condition, not a conditional, why is my mind like an if statement, right? I'm saying like if this thing is true, if unemployment is greater than the unemployment mean, when I put parentheses around that, if that statement is true, it's going to put a 1 in for that high on that variable. If that statement is false, it's going to put a 0. So essentially what this will do is every county where the unemployment in that county was greater than the mean, it'll put a 1 into the variable for that. Every county where that wasn't true, where they're actually the mean or lower, it'll show up as a 0. Okay? So I'm going to run this line of code. You can kind of see here, sure enough, when the unemployment was above the mean, this variable becomes a 1, this new variable I created. Anytime it was below the mean, it's a 0. Yeah.
So what would happen if you put gen instead of egen for the previous slide of code?
Oh, when I was doing the mean? It will get mad and say, well, in fact, that's not really the error you can see. So I want to make sure I'm acting. So I'm going to drop it. So if I try to just use the gen command here, unknown function. Because the whole thing about putting that E in front is it's telling Stata, I'm going to give you a function name. In this case, if we go back to the code, it was like the blue mean word. It doesn't know what that is, but when you put egen, it knows that it's supposed to be looking for that function in a set of functions that are stored behind the scenes. Could they condense those two commands? I think yes. I'm not good enough with computer programming to suggest to them how to do that. And maybe there's a very real reason why they don't. But I understand why it seems kind of stupid. But it is, anytime you're pulling, like you're trying to use a function that's just built in behind the scenes, you have to use that egen.
So do we have like a list of functions that are built in, like what we know?
Just we'll work through them. I'm never gonna like expect you to know which one you have to use. You'll have an example of it in a do file, but generally, especially starting out, the mean, standard deviation, function we used last class, median, it's not gonna be a ton. for these first couple weeks. Eventually, I might start showing you kind of how we use, I'll show you stuff that I don't expect you to know how to do, and there might be some other kind of things that are built in there, but yeah, it's only gonna be a handful starting out, and you should be able to kind of identify them just from the do files that we go through in class. Is that, I know there's not like I can, you know, actually I can put a list up, because you could, if you go to Google and you search Stata ECON functions, I know that there's a Stata list that provides all of them. It's a really long list and you're not gonna need all of them. But yeah, I can get a list up there so you just have some idea. Yeah. Good question. Any other questions we can get in here? Okay. So, I don't need this variable again. I already created this. So I'm now gonna go to just like, I wanna look at this high up on it, because I know I had this long right tail. So I'm kind of a little bit worried that maybe it may not be it's not an even split. I shouldn't have 50% of the counties as a 1 and 50% as a 0, because that mean was impacted by those extremely high values. So I just want to take a look at what the actual values for a variable are. I can use this tab function. Now, it makes sense for a variable like this, because what tab will do is tell you the number of observations for every single value that's in the data set. Well, for this variable, the only two values were 0 and 1. So if I run tab here, it's going to give me this output. It doesn't, once again, when I'm using this, it's just giving me output. Anything that shows up in this screen isn't being saved any. Right? So I can look at this, but if I want these numbers, I got to copy and paste them or write them down somewhere, because once I close this file, or once I close this program, it goes away. So I can see here though, I've got what? About 45% of the counties have above average unemployment, and 55% have below average or below the mean. Okay? So that can give me kind of a nice quick idea about like what these two groups, how many are in each one. Now, what's not useful, let me look at one. Let's say I just try to do, let's say I try to tab that unemployment. What it's going to do is it's going to say, here's how many observations have an unemployment of 0.1. Here's how many have 0.2, 0.3, 0.4, all the way to the very last one. So I can run this. Excuse me. But I mean, it is kind of useful. I can see that, there's higher frequencies for the values in the 2s and the 3s, and even the 7s, and it like really tapers off. There's some county that had 28% unemployment, which is wild. But it's not quite as helpful when I have like a more continuous variable. But for these discrete variables, are these what we call indicator variables. So when I'm creating these 1, 0 variables, a lot of the times I'll reference them as indicator variables. That high unep is indicating to me, if it's a 1, that the unemployment rate was above average. If it was a 0, it was the average or below. Okay. Any questions on that? Okay. I could also like summarize, if that's too much to look at, I can summarize things. Okay, it looks like, the proportion of times this high unemployment rate variable is 1 is about 0.45, 4488. This is a different way of looking at it. If I have a 1, 0 variable and I take the mean of it, why does that match up with? Now I have all this stuff that I showed you. Why does that match up with the percentage I was getting here? Think about a 1, 0 variable. I'm calculating the mean. What's in that numerator? I'm adding up every single observation's value for X. So I'm adding up the first county, maybe it's a 1, and the next county's a 0. Well, adding 0 doesn't change anything. So my numerator of the mean is just going to represent the number of counties that had above average unemployment. Because anytime they didn't, I was just adding a 0 in there, it didn't impact my numerator at all. So if I ever have these indicator or these 1, 0 variables, when I'm adding up all the values, I'll just be adding up 1s every time it was a high unemployment rate county. And then I'm going to divide by the total number of observations. So if I have the total number of counties with high unemployment, total number of counties in the data set, that's always, the mean is essentially going to give me what we call a proportion, right? It is still a mean, but because it's for a 1, 0 variable, we say it represents the proportion of counties that have high unemployment rate. Because when we have a 1, 0 variable, anytime, We had it at 0, nothing's getting added to that numerator. Okay. Any questions on that idea before we push anything? Shouldn't be too bad. So I think I wanted to do, you could do this with low unemployment. It's very similar. I just have some additional code. We don't really need to, I don't think, kind of waste time on this, but I could do the same thing. Say, if it has below the mean, create this low unemployment rate variable. You can run more than one line of code, so I just selected all 3 here. So it created this low unemployment rate variable. Notice, oh yeah, most of the time it's the 1 when the high unemployment rate was 0. That's how it should be, right? All I did was I just flipped that kind of relationship, right, with the unemployment below the mean. And then I can kind of look at how many counties had low unemployment, about 55%. What was the proportion? I can use that sum, and that mean really represents that proportion of counties with low unemployment as well. So then the idea is I can do these conditional means, okay? So what I might then be interested in is, okay, what was the proportion of people that voted for Trump in these high unemployment or these low unemployment rate counties, okay? So I did this kind of out of order, it looks like. Did I not? Oh, I must have added some stuff in. So I might save some of this for next class. So we're just going to be looking at the unemployment rate one. So I had multiple lines. I think I chose to not go with kind of racial categories, and I chose the unemployment for the example here today. So I'm going to use this by sort command. I'm going to say, okay, by this low unemployment rate variable. So what by sort does is it is going to group the data based off of the values for that variable. Well, here for an indicator variable, there's only going to be 2 groups. All the counties that had low unemployment and that had a 1, and all the counties that had a 0 in that low unemployment rate variable. So it's going to separate the data into those 2 categories and then give you a summarization. We used this last week, this sum command, summarize. It's going to summarize this Trump 2020. So this is going to say, if I run this code, it gives me 2 different groups, and it says if I look at all the low unemployment rate counties, the proportion of those counties that voted for Trump was about what, 0.63 or 63%. In the non-low unemployment rate, or if you want to think about kind of high unemployment rate counties, the proportion of people who actually voted for Trump was about 0.67. Right? So actually, I think this is reverse of what I thought I said earlier, because here we actually have that the low, or no, I think this is what I said. The low unemployment rate counties actually had a higher proportion voted for Trump, right? 67 relative to 63 in the kind of non-low unemployment rate counties. Now I could create all types of groups here. So this is the other one that I had. I think I just did it out of order, but I could do, is it a high proportion of that county's population considered white, right? I just said put a 1 if the kind of proportion, or sorry, not proportion, percent of the county that was white was greater than 80. So I have this variable here somewhere. Yeah, so it's got all these different like racial categories, and the percent of that county is that racial category. So I just chose like extremely high prevalence white counties, so ran that code. I could then do the same kind of thing up here and summarize that variable. And now I've got, okay, for these counties that don't have a high proportion of their population being white, the proportion that voted for Trump was about just under 60%, right, or 0.59. But these these counties that were highly, a very large proportion of their population be white, 70% of them voted for Trump. So we start to pick up these conditional mean differences just by creating these different groups. So very basic, easy way to do that, just creating what we call indicator variables, then using this by sort command to look at kind of the differences in means between those 2 groups. Okay. Set. Any questions on that before we keep moving? So my code's a little out of order here. I guess I probably should have put this up further up here. And doesn't matter. It doesn't have to be. Your code doesn't necessarily. Where did I put it now? Hold on. There we go. Your code doesn't necessarily have to be in order, right? Because you're highlighting it and executing it. So it probably makes a little more sense if it's in order to somebody else. So we kind of have it up there before we did that here. You can also do things just to kind of to show you another way of getting at the same thing. So after I created this indicator variable, this low unemployment rate variable, if I use the same by sort command, instead of using this sum, because the sum was just giving me the output in that program and that all goes away. I could actually create these group means, right? So I'm gonna say, okay, look, I wanna create two different group means, which is what was the proportion that voted for Trump in these counties that had low unemployment or a 1 for that variable, and what was the mean when it was a 0 or it had high unemployment. So you can still use these ECON commands. So by sort, right? Sort the data into these two groups, low and high unemployment rate counties. Calculate the mean, right? Using that ECON, right? I'm going to use that mean of the Trump 2020 variable, and it's then going to store that in your data set, right? Which you then can save. So if I sort here, I'll run this code. Now I get this variable. And now notice for all these low unemployment rate counties, here's my proportion that voted for Trump. And then I've got to scroll down. Now it was by sort, so it sorted the data by that variable. Now for all these low unemployment rate counties, here was the proportion that voted for Trump. We can kind of see 0.67 versus 0.63. So just another way of getting the same information, but then this information, if I then go to, and I want to make sure I don't write over my the data here, but I will show you, I'll do a temporary one. So if I go to file save from the program, call this in class 9.3. I can actually save my data set, right? So if I go, if I don't crash the program here. So I can actually save this data to my OneDrive as well, and it will have this variable that I calculated the mean stored in there, so that if I ever want to go back, I can still look at it. When I was just using that summarize command, all of that, when I close the program, is going to go away. Okay. So now I'm going to show you also, we can go to file open. If I just want to open a regular kind of set of data set, or we'll call it a .dta file, I can just open those up as well. And now notice it's got that group mean variable still saved. Okay. Now, it's good to save data sets as you make changes, but I would always not name them the same thing as the original data, because you don't want to write over the original data. So if you want to start saving your work, I would call it something a little bit different, or like whatever the file name I gave you was, and then maybe your initials at the end, or my work, or something that identifies like I can save this data, this .dta file, but I'm not writing over the original data. Okay. All right. This yet. So we'll come down here. So I did that white summarize, not to. So let's look here. I just want to show you. So I'm going to create this. We had this high white population indicator. I'm also going to create a high income indicator. So it's just if the average income in that county was greater than 75,000. Create this income high variable that takes on the value of 1 if that's true, 0 if not. So when we're doing these conditional means or conditional statements, we don't have to just use one, we can use multiple. So here I want to create this new indicator, right? So I put these kind of statements in parentheses, but now I'm going to use two different conditional statements. If this income high variable is not equal to, so we don't have like a not equal to sign in Stata. If you want to say not equal to something, you put an exclamation point and then an equal sign. So this is going to create a variable that if the county is not considered to be high income, or it has a very high white population, then this is going to become a variable that's going to become 1. So think about this is going to be the counties that high income white county. So actually, well, this name doesn't make a whole lot of sense, but this is going to be any county that has not high income and kind of has a high white population. Or sorry, not and, or. So if I want to use or, I use this kind of vertical line. If I wanted to create a 1, 0 variable where both these things are true, then I would use an and sign. So we can use multiple conditional statements to kind of break these down based off of several variables. Here, I'm going to kind of use that or. So if it's a high white population county, or it's a essentially not a high income county, so this is going to be like high white populations, lower class, probably thinking about like some of these rural Indiana counties, then this is going to become a 1, 0 if not. So now if I do this and summarize that variable, just kind of interesting. Well, now we can see there was, these counties that were considered either low income, right, not high income counties, and a high proportion white. The average proportion voting for Trump was 66 relative to not belonging to those groups, 0.43. It's a pretty dramatic difference in voting behavior. So we can start to use these conditionals and these group means to just pick up like, well, what characteristics are causing voting patterns to be a certain way, right? Now we can actually go more, dive deeper into it, make it more complicated. But this is kind of a quick, easy way of looking at it. Okay. Any other questions? All right, so we'll save this, I think, for Thursday. I'll even kind of pick up on that. Come back to the slides. A little bit of time left. I want to introduce this idea, and we'll really dive into it on Thursday. So we talked about these normal distributions and the standard normal distribution. So that was kind of assuming we had population data. A lot of the times we don't have population data. Even if we have really large data sets, it's let's say I'm interested in the average income in the U.S. There's a lot of unreported incomes, right? There's a lot of people don't, so I might not be able to even access that data. So I might always have what we call sample data. Okay, so we're always going to hopefully have random samples, and we'll talk later on about the problems that exist if we don't have random samples. But for now, we're assuming that we're able to kind of randomly sample from the population to get this sample data set. So this could be, maybe I only have data from 20 of the 50 states. Maybe I only have 100 of the however many thousand students there are here at IU, right? So I'm going to have a subset of the population. This could be individuals, state, countries, whatever the example ends up being. We're going to think about it as we still notate it as every single observation in my sample data. So Y1 would be like the value for this Y variable for the first observation of my data set. Y subscript 2, this is the value for this Y variable for the second observation. It's just like we were doing with population data. No real difference there in the notation. Now we're also assuming that each one of these observations we selected were selected completely independently, or what we call like IID, independently identically distributed, right? So this is the idea that if I'm selecting students from IU, I chose someone at random. Well, they had a sibling that went here, so I used the sibling as well. That wasn't completely random, right? Those two siblings are going to have characteristics in common that they might not with another random student that if I was to completely choose a student at random. So we'll talk about how sometimes this gets violated, but for right now, assume that we're completely randomly selecting these different observations in our data set, such that it doesn't matter who I selected first. The expected value for this Y variable, the person I select second, is still the mean. The expected value is still the mean of that variable because I'm choosing it completely at random. I don't know who I'm going to be getting. So this is kind of our setup. So we can think about when we're calculating our mean, we said we were adding up all the values for Y and dividing by the total number of observations in our data set, which was capital N. For our sample size, we'll notate the size of our data set. Instead of capital N, it's going to be lowercase n. Just represents the total number of observations in our data set still. It's just, identifying its sample data. Now, I wrote this a little bit differently. Yes, we're dividing by n. Anytime we divide by something, it's the same as multiplying by 1 over that. So some of this stuff I'll show you throughout the semester. I'm going to use kind of different that notation where instead of dividing by n, I'm just multiplying it by 1 over that. It's the same thing mathematically. Okay? Now, this might seem intuitive, but if I completely randomly, if I take a sample of 50 random students and I calculate their GPA, write that number down. I then take another random sample of 50 students, calculate their average GPA, write that number down. I do that like 1,000 times. If I were then to take the average of those 1,000 different averages, it's always going to be whatever the original population mean was. They'll always be centered around whatever that true population mean is. And I'll walk you through, prove this to you with data next class. We won't have time today.
But I don't know, it kind of makes it intuitive. I'm kind of randomly sampling. It should be that the mean of my sample means ends up being the population mean. Now, what'll also be true is the variance won't simply be my population variance. So if I were to take 1,000 different sample means and then I were to look at the variance of those sample means, well, if you think about it, when I'm taking a group of 50 students and I'm calculating the mean, automatically, I'm not gonna see these, like if I choose any one student, I might see a GPA of 0.2. If I choose 50 students at random, I'm like, pray to God, I don't see an average of 0.2, right? So by taking this mean, because it's of a larger set of individuals, the tails of the original distribution I was sampling from, I'm not gonna be seeing those values for the averages or for the means. So our variance on our sample means will always be the original, it is influenced by the original variance that exists in the data I was sampling from, right, in the original individual student GPAs. But as I take larger and larger sample sizes, I'm not as likely to see those extremely large values for my sample means. So the variance of my sample means actually ends up being a lot smaller. It's the original variance in the data I sampled from, but as my denominator gets larger, as my sample size gets larger, it's going to be getting smaller and smaller, closer and closer to zero. In fact, if you think about like, if I were to like take a sample the exact same size as my population mean, well then there is no difference. I'm always going to see the same population mean if I could truly get everyone in the population into my sample data. So as we have larger and larger sample sizes, we're really reducing the variance for those different values we see for the sample mean. We'll talk a lot more about exactly why, but this is a good thing for us, right? You gotta think about it. You know, if I only have 50 students instead of 500, well, that sample mean from 500 is more likely to be close to the true population mean than if I only had 50 students, right? Just having more data, it's always a good thing. I can always be more likely that I'm getting accurate values of what the population parameters actually are. So kind of the terminology for this is the law of large numbers. Kind of says that, you know, as long as, we'll get into it later, but as I take larger and larger sample sizes, my sample means become a consistent estimator of what that actually true population mean is. So we'll use this idea, and I think I've got the numbers here, but I'll kind of foreshadow a little bit. What we're going to start out with next class is probably start out with Stata right away. I'm going to run a bunch of simulations with some MBA data, and it might seem dumb, but it's just because I had the height. So I was like, oh, I need a height data set. I could go out and grab this huge height data, and obviously the mean is going to be a little bit different than the average population. But we can randomly sample from this data set, create all these different sample means. And remember, I was using things like that HIST function. We can then look at the distribution of those sample means. We can calculate the mean and the variance of those sample means, and we'll see that it holds up with those formulas I was showing you before. That the mean of our sample means will always be true population mean, and the variance will always be the variance of our sample means will always be the variance of the data we sampled from divided by our sample size. So I'll walk through a proof of that, kind of using Stata. We'll then kind of dive into more like confidence interval hypothesis testing, and hopefully by the end of the day, Thursday, we'll kind of finish review. Well, we're going to dive into linear regression, but I'm going to go through that much slower, not as much as review, because I'm going to bring up things that probably weren't brought up in your 370 classes. So last day of review is going to be on Thursday. We're then going to dive into linear regression next week, and I'll start to probably overlap a little with 370, but introduce some new ideas as well. All right. You guys have any questions for me? Kind of hang around for a little bit after class. If you have any problem with Stata, try those two things I mentioned, and it's still not working. Try to stop in during office hours tomorrow, and I can kind of maybe give you some one-on-one help there. All right. All right. I'll see you guys on Thursday.